Hello there, welcome to today's lesson. This is lesson number 9. If you're following along, it starts on page 67 of your book. And here we are going to talk about something that, well, I'm not going to lie, it's a little challenging. It's congruent figures and proof outlines. Everyone has not so fond memories of having to do mathematical proofs in their day. I don't know if schools even teach this anymore, but today we're just going to start with proof outlines, not the total proof. So don't worry, okay? It's not going to be that bad. It's going to be great. However, I do have Michael Scott throughout the lesson being a little negative, so he might be expressing how you feel. We'll see. Okay, first of all, I stayed up all night wondering where the sun had gone. Then it dawned on me. Okay. Okay. All right, let's start right away. Okay. We remember that in math, this is going to start out easy, okay? We're going to start with the words equal to. That means that 4 and 2 plus 2 is in the same location on the number line. That's what that means. It's the same idea, the same spot, so those things are equal. We have greater than, and we have less than. Less than is to the left on the number line, greater than is to the right on the number line. And the number is the idea that it represents. Okay, it's like the tiny little infinitesimally small spot that it actually represents on the graph. All right, let's go to the next part. I know Michael Scott is already like, this is the worst. Congruent. When we say two figures are congruent, that means that they are geometrically equivalent. So these things are congruent. A segment that's two segments long, and a line segment here that's 2 segments long, even if it's going in the other way. Same with angles. This one's 27 degrees, this one's 27 degrees, so those are congruent. Okay, and then we have 2 triangles here where the corresponding angles of the triangles are congruent. Okay, and the sides have equal lengths, 3, 4, and 5, 3, 4, and 5, so they are congruent. And remember, if you can pick up a geometric figure, like pick this up, here, I'll do it. Let's pick it up. Okay, if you can pick this up and you can mentally flip it, turn it, I could even do like a mirror image of it. I don't know if I can do that with this, but oh, I can. Look at that. That's cool. All right, if you can do that to it and then the figures match exactly and put it on top of something else, right? Then you can say that they're congruent. You know, I didn't draw them exactly congruent, but you know what I mean. Okay, and then it turns out that all 3 of these triangles right here are similar because the lengths of the sides in this triangle B, are twice as long as these in triangle A. So if you take the 3 and double it, you get a 6. If you take the 4 and double it, you get an 8. 5 doubled is 10. And so that means that this is a scaled factor. Triangle B is a scaled factor of A. And you could say that the scale factor from triangle A to triangle B is 2. Or you can say the scale factor from triangle B to triangle A is 1/2. Okay, and then the lengths of the sides in triangle C have exactly the same lengths as triangle A. So the scale factor between angle C and A, or A to C, is 1. And so you can see that, okay, so these are similar because you can shrink it or scale it and it'll be exactly the same. But these are congruent because they're literally exactly the same, just flipped. Okay, so remember, congruent is exactly the same. Similar means you've shrunk it, you've given it a scale. Okay, congruent triangles, they point out that congruent triangles are actually similar triangles also. It just means that the scale factor is 1. So if you're shrinking or growing this to this, what's the scale factor? It's just 1. I mean, that's silly. It's kind of stating the obvious. What about a postulate? What is a postulate? A postulate is a noun, right? It's a statement that everyone accepts without proof. But you can also use it as a verb. You can postulate something, like you can make a statement that everyone accepts without proof. Okay, so we're going to go on to learn 4 different postulates of triangle congruence. I know, are you looking at me like this? I'm dead inside. The first one is called SSS. SSS, and SSS stands for side, side, side. All right, so here we have, okay, let's start with here. Here we have 3 segments. One is 2 units long, 3 units long, 4 units long. In the center figure here, we've made a triangle by using these segments. So we used side 2 here, the 2 is at the bottom. And then we put the 3 here, and then we put the 4 here. In this figure over here, we also made a triangle out of these sides, but we put 4 as the base. And then this one's going to be 2, and this one's going to be 3. If you mentally slide over and rotate this triangle, it will cover this one exactly. Oh yeah, look at that. It covered it exactly. Woo! That was cool. Okay, that means that these 2 triangles are geometrically equivalent. And the same would happen if we used side 3 as a base and made another triangle, but this one was the base and the other segments had lengths of 2 and 4. Then you could flip that triangle and you could put it right on top of all of these other ones. Cool. All right, so that's called the side, side, side postulate. It's basically saying that if you make a triangle with sides that have the same lengths, all triangles constructed whose sides have the same lengths as the given segments are going to be congruent triangles. There we go. All triangles that are made with sides that have the same lengths are going to be congruent triangles. They will fit right on top of each other. Okay. Next postulate is the SAS postulate. This is side, angle, side postulate. Okay, the whole idea of these postulates is, are you going to make congruent triangles? That's going to be the question. Are we going to make triangles that are congruent? Congruent. Do they fit right on top of each other, right? And turns out if you do the side, 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 so they all have the same lengths, then they're going to be congruent. There's another way to get congruent triangles. It's the side, angle, side. So all you need is a side that is the same, you need an angle that's the same, 25 degrees, and then another side that is the same. And if you have side, angle, side the same between 2 triangles, that's all you need to know. The triangles have to be congruent. Okay, let's do a third one. Why are you the way that you are? I know you're wondering this at this point, huh? The ASA. ASA means a different thing to me because I'm an anesthesiologist, so it means the American Society of Anesthesiologists. That's what that means to me. But in math, it doesn't mean that. It means angle, side, angle. This is the third postulate of triangle congruence. Angle, side, angle, or ASA, not American Society of Anesthesiologists. Okay, all you need is an angle to be the same, a side that is the same, and another angle that is the same, and then you have congruent triangles. And sometimes students are confused by this because they think that the side has to be between the 2 angles. It does not have to be between the 2 angles. It can be any freaking side. So angle, side, angle, and this can be any side. As long as you have an angle and one side and one angle that is congruent between 2 triangles, then you have congruent triangles. Bam, easy as that. All right, so the triangles are congruent even though the side is not between the angles. Because, why? Because you've got 2 angles. That means the other angle has to be the same because they have to add up to 180, right? So you could call this the angle, side, angle, angle postulate, Why could you call it that? Because of course the other angle has to be the same, has to. So it could be the ASAA. I feel like we're gonna write a bad word in one of these postulates. Maybe not, I don't know. All right, the last postulate of congruent triangles, I know you're thinking you are a thief of joy at this point, is I call it the heck, because it could be, if you just said these letters, HL, it could mean something else, and you might remember it that way. But it's actually the last postulate, so you're not in heck. It's just the hypotenuse leg postulate. This is the fourth postulate of triangle congruence. What the heck does that mean, a hypotenuse leg? The hypotenuse leg only pertains to right triangles. It has to be a right triangle, has to have a 90-degree angle in it. Why? Because a hypotenuse is always the side opposite the right angle. It's that side. And so you can't have the hypotenuse if you don't have a right angle. There's no hypotenuse. The hippopotamus sits on the opposite of the right angle, hypotenuse. Okay, so here in this figure on the right, what the heck do we have going on here? Well, imagine you have a ray here. Okay. I really messed up my explanation of this, but the basic idea is that if the hypotenuse of a right triangle has the same length as the hypotenuse of another right triangle, as well as the length of one of the legs, then those triangles are similar. That makes total sense to me because if you think about the Pythagorean theorem, which applies to right triangles, a squared plus b squared equals c squared, if two of the lengths are the same, so the hypotenuse is c squared and one of the legs is the same, then the other one has to be the same. So it's the same based on the SSS postulate. But this is a whole new postulate that just simplifies that, and it has a different explanation, but it's called the hypotenuse leg postulate. So the HL postulate, you can use that in your proofs if it's easier, but I also like the SSS postulate and the Pythagorean theorem. So there you go. Okay, so that's the fourth and the last triangle congruence. All right, let's move on to proof outlines. Now that we know how to prove that triangles can be congruent, you can learn how to do formal geometric proofs. A proof is like, I'm going to prove that this is mathematically true, or I'm going to prove that these triangles are congruent. Many of the proofs that they require you to do in math require that you have to prove that two triangles are congruent. So the first thing we're going to learn is how to do a proof outline. Because then the formal proof is just like expanding out that outline a little bit more. You have to remember a couple of symbols when you're doing proofs. This means congruent. This means perpendicular to. So segment DC is perpendicular to segment AB. This means congruent over here. Segment AB is congruent to segment DB. And then this means parallel. So segment MP is parallel to segment QR. And you can also write it without the little line on top, and this still means segment DC is perpendicular to segment AB. Also say it like this. You can say PQ is equal to 5 centimeters, and that means the length of segment PQ is 5 centimeters. And you can also write this. Triangle ABC is congruent to triangle DEF. And remember, just like we learned in the last lesson, when you write statements of triangle similarity or triangle congruence, you have to be careful to list the vertices in order. So A has to go with D, B has to go with E, C has to go with F. All right, let's start with an example. This is example 9.1. It says given, so this part's given. They're going to give you some information, then they're going to ask you to prove something. That's how it works. So you're given this information over here. Given that AD is equivalent to BD, and DC, that means this one, is perpendicular to AB, outline a proof that shows that AC must be congruent to BC. They want these to be equal. Okay, so they want you to prove that this is the same as this. So when you're asked to prove that two line segments are congruent, the easiest way to do that is to prove that the triangles are congruent. If the triangles are congruent, then obviously those segments are going to be congruent because you'll be able to put one right on top of the other. you only need 3 steps. The first one is to write this image in your homework, in your notes. Write it down. Copy it exactly. And then we're going to use tick marks to indicate sides and angles that are equal. Step 1, the first thing that we're going to do is mark this one with a circle. Why are we marking that with a circle? Because we're marking the segment that is a side in both triangles. And so obviously they have to be the same because they're a side in both triangles. Second step is that we're going to prove that triangle ADC is equivalent to triangle BDC. Let's make sure that we got those angles correct. So A goes with B, and then D, and then C. Okay, so that's fine. Why are those triangles congruent? Our proof is SAS. So we're going to use the SAS postulate to prove that they're true. So the side that is the same as this side, the angle that is the same is this right angle because we're given the fact that that's perpendicular. The other side that is the same is this one because we're told that information that AD is equivalent to BD. The third step in the proof is this. I'm not going to write it again because it's right there. And it's that segment AC is equivalent to segment BC. And the reason is CPCTC. And this stands for corresponding parts of congruent triangles. Congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. Instead of writing all of that out, you can just use CPCTC. So this is your entire answer. This is why proofs are hard, because you can just write like a number 3 for your answer. The proof is like showing your work. You have to show your work because that's how you get it. It's like as if you're a lawyer and you're presenting a case to a jury. You can say, well, my first piece of evidence is that this side is the same, and that this angle is the same because they say it's perpendicular, and we're given that AD is the same as BC. And therefore, these triangles are congruent based on the SAS method. And therefore, these segments must be congruent based on CPCTC. And that is my proof, ladies and gentlemen of the jury. And there you go. That's how you do a proof. Are you freaking out like this? Okay, example 9.2. We are given this information and we have to prove, they want to obtain a proof, outline a proof that shows that DF is equivalent or is congruent to DG. Okay, we're getting a little harder now. This proof outline only has 3 steps again, but the first step is going to have 2 parts. First, copy the figure down and use tick marks to indicate the parts of the figure. Use tick marks to indicate the parts of the figure that have equal measures. So they tell us, I'm going to erase that because we don't know that yet. We know that this angle is the same as this angle. So I'm going to mark that the same. We're also given the information that EF is equivalent to GH. Okay. All right, so that's what we know. That's the first part. Now, look at the figure and study it carefully because you're going to have to figure a couple things out. We know that these guys have this angle and this angle is the same. They have equal measures. And if you look, they are the base angles of this big triangle. So that means the big triangle is isosceles. And the sides opposite of these congruent angles have equal lengths. So now, because we know that, we can say that this side is the same as this side because the big triangle is isosceles, those have to be equal. Now that we know that, we can do part 2, which is that angle or triangle EDF is congruent, triangle EDF. So where's that? That's this. EDF is congruent to HDG. To triangle HDG, and I got those angles right. How do I know that? Side angle side. I can use any of those postulates as evidence. So this would be a side, an angle, and a side that we know is the same. Sweet. Once we got to there, then it's easy. The last step of the proof, ladies and gentlemen of the jury, is that segment DF is the same, or is congruent, I can't get that right, is congruent to DG. And what is my proof of that? CPCTC. Congruent triangles, congruent sides. Whew, that was a good one, right? You're feeling good about it now? Let's do example 9.3. This is the last example, so pay attention because this is going to be the most complicated, right? We've got this figure right here. Sorry, it's not a great picture. The first step is to copy down the problem and write down what we are given. All of this information in white is what we are given. So we know segment AG is congruent to EF. Okay? And then they also tell us that CA is congruent to CE. I'm just going to put that up here. We also know that B right here is the midpoint of CA, and that D is the midpoint of CE. So if you have two sides that are equal and you cut them each in half, that means that this side is congruent, this little side, each half is congruent, right? This is congruent to this, and this is congruent to this, and they're all congruent to each other because you just cut them in half. So I can do that actually. Now, the whole point is we want to prove to the jury that BG is congruent to DF. Where's BG and DF? Oh, we want to prove these sides are the same. Okay, no problem. We can do that. We can convince a jury of that. In order to show that these are congruent, we have to prove that these triangles are congruent. They already told us that this is the same, AG and FE, and we can also prove to the jury that this angle is the same as this angle. Why? Because they told us that AC is congruent to CE. And this is congruent to itself because it's the same freaking line. So if we look at this big triangle and we have one that's the same line and then we have these that are equal, that means this angle has to be equal because this is another isosceles triangle. Sweet. Okay, once we know that the angles are equal, what do we have here? We have side, angle, side, side, angle, side. Sweet. So now that we can say for step 2, that triangle ABG is congruent to EDF triangle because of the side angle side method. Okay, so if the side angle side method is true, that means those triangles are congruent, and now we can say that BG is congruent to DF because of the CPCTC. Corresponding parts of congruent triangles are congruent. Bam! We did it. Oh, where's Michael Scott? I thought there would be another GIF. Better. Yay, he's finally happy. He's happy this is over. All right, good luck with your homework. Love ya. Bye.